posting these videos in Blackboard, so cheesiness ensues. Okay, so the mean, as in the mean math teacher. Just kidding. No, of course. What in statistics? What is a mean? The average. Yeah. So the mean is the average. I think that they just gave it this name because they want to be able to say mean, median, mode, and they all begin with M. I don't know why. So the average. In this class, there's a common symbol we're going to use for it. It's denoted X with a line over the top. And I'm afraid you've done so much math occasionally, I say these things without explaining them. This is red X bar, okay? So in this class or other statistics classes, people will say, oh, what's X bar? That means the mean or the average, okay? And I'm going to show you some fancy math notation for finding the mean. So you guys know how to find averages. You add the values all up and you divide by how many, right? Okay, so here's the fancy math way of saying that. X bar equals, we're going to do Greek letters now, capital sigma, okay? You guys seen that letter before? Yeah. Yeah, so Greek letter, I think it's capital sigma, X sub I over N. So blah is sigma. What do you think sigma stands for in this context? Sum. Yeah, so sigma means sum in math. This means sum up all of the values that you have. And n, we talked about yesterday, was your sample size, which you could also think about as how many, right? So just so you have a little bit of experience with that whole sigma notation. You'll see it a little bit if you do statistics past this level, but it also comes up in your book a little bit. But it just means add them all up. And they occasionally have numbers on the bottom, like it might say I equals 1 to 10. That would mean add up the first 10 things. Like first plug in 1, then plug in 2, then plug in 3, and add them all up. Tells you where to start and where to stop. And if you get into calculus 2, there'll be an infinity on that thing, and you add up an infinite number of things. So just if you're going there someday.
There's also ranges.
Yeah, exactly. Okay, so that is the mean. What is the median? The middle, yep. This is the middle value. Now the kicker is that your list has to be in order, because if your list isn't in order, the middle could be something totally random, right? You could get different middles with the same list. So the middle value on an ordered list. What happens if you have two middles? So Q. So what if two middles? Answer, we'll use fancy words. Find the mean of those two values, right? Or take the average of those two middles. Okay, on the next example, I'm dreaming I have a class of 7 instead of, it's not at all, class of 7. Okay, so class of 7 students, find the mean and the median. So if you have a calculator, take it out, because it's good to actually try to test these things. You can use your phones, I won't take them away, I promise. So X bar will equal, so add all those numbers up and tell me what you get. My goodness, I didn't add them up. I just gave the answer. That was silly.
The sum is 592.
5. Do you guys agree with that? Anybody else got a good way to check if you're right is to do homework with a friend, and then if you get the same answer, you're probably correct. As long as the answer wasn't obtained by you copying their answer, of course.
Got the same.
Got the same thing, and then over 7, okay, great. And that's not going to be a whole number, so divide it and round to the nearest tenth, as in 1.
84.57.
So 84.57 would round to 84.6. And if I don't specify, you really can round however you want. So on homework and quizzes, I'll try to specify how I'd like you to round. Just a warning, on your quizzes, I cannot let you use your phones as calculators, for the obvious reasons that they Google stuff. and I can't babysit you Googling stuff. It'd be like impossible. So you have to actually have a calculator. And can I borrow yours for a second? This is a great one to have. It's a TI-30 and it's like $20. You don't have, doesn't be fancy. And if you have a graphing calculator and it's fancier, no problem, okay, don't care. But this would be a cheapo option if you want an option, okay? But you need a calculator that's not your phone. Because I'm not gonna check if your phone is in airplane mode and remains in airplane mode, la 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 la, too much. Okay, so median now, we need to order them. So who was the suckiest? Politically correct. Who was the lowest score? 60. Not suckiest. Sorry, I probably shouldn't be so mean. Okay, who was the next lowest score? 79. Okay. 86. Yep. Okay. 89. 91. 94. Okay, and this one, because there are an odd number of things, we actually have a middle, so the median is... It occurs to me that I don't know if there's a symbol for median. I don't know. And I wouldn't use M because lots of things begin with M, so just say median equals or just list 89. So, okay, great. I suspect you already all know those, right? Okay, maybe not the sigma thing. Okay. We didn't discuss this a lot, but so outliers are variables that are like way outside the other range of values. So if I had that previous list of test scores and somebody got a 10, that person's a little bit like separate from the rest of the people, and I shouldn't judge myself too harshly for their 10, right? Because something special is going on. So what do you think? What measure of central tendency, so these things, the mean and median, are called measures of central tendency, like the middle. Which thing is impacted more by outliers? Like if you have a value that's like way off all the others, the mean is affected more. Yeah, the mean is more affected because the thing is it changes the total sum. And so what measure of central tendency you use depends on your context. If you are talking about, like typically for like houses, they report the median home value because there are so many homes that are large and expensive and are outliers. Does that make sense? And I think the same thing actually is often the case when they report like median income. There are many incomes that skew things and make it seem like they're better than, like if you've got a lot of those that are higher than the majority of the incomes, that'll make it seem like the average is better than it actually is for half of the people. So what you use depends on the context, but the outliers are big or extremely big or very, very small values affect the mean more than the median. Okay, so here's an example. Suppose your grandparents died at the following ages: 25, 70, 80, and 90. Which do you think is a better indicator of how long you may live, the mean or the median? Let's actually find them to show how different they are, okay? So x bar, what's that going to equal? I didn't do this on my notes, so we should 25 plus 70 plus 80 plus 90. And I should have brought a calculator, but I emptied my backpack today, so make you pay. Okay, so 66.25. Do you guys agree with that? Okay. And then the median, that's going to be 75, isn't it? Because we have 4 values, so we need to average the 70, 70 and 80, yes? So which do you think is more like a better indicator? Yeah, probably the median. As 25 is, so I would say not consistent with the data or consistent with the other numbers.
You're talking about the 0.25, right?
Yeah, probably the median as the value of, how's that? With the other data values.
Can you not say that it's an outlier yet because you haven't proved it yet?
We have, there's no hard and fast rule for what is an outlier and what isn't. We're going to have one thing we're going to learn today about one method of saying a point is an outlier from Mises criteria. So you could call it an outlier and I wouldn't be like frustrated with you because it is definitely seems to be very different than the others. But there is a specific criteria we're going to talk about that will let us identify them based on that criteria. But there's no super hard and fast rule for that is consistently applied. What might have been that 25-year-old person's, what might have happened to them? Car accident. So like my husband, his grandpa died in World War II. I mean, he's Russian, and so like if you read about World War II, lots of young Russian men died in World War II. So some kind of tragic something happened to that person, basically. So, not put a damper on the mood or anything. Okay. So here we go, describing spread, something called the interquartile range. So I know I kind of rushed through this a little bit, so let me kind of do a little bit of review of what we talked about last time. So we had these numbers. We had the min, quartile 1, the median, quartile 3, and then the max. The word quartile comes from the word quarter. Quarter means divide into 4, right? Okay, so roughly speaking, between the min and quartile 1 are the first 25% of values.
How do you spell quartile?
Quartile. You shouldn't trust me all that much on spelling because I'm a math teacher. I can't spell check on the board. It's going to happen at some point in time. There's I spell something wrong. Between quartile 1 and the median is the next 25%. So how much from min to median? What percent of the data? 50. About 50. This is another 25%. So there's the first 75, right? Makes sense? And then this last thing is an additional . So where does the middle 50% fall between? Q1 and Q3, right? How about the upper 50%? Median and max, right? Okay. So range. Now the range is how far is it from your lowest to your highest value? So the way to find the range is to do your max minus your min. Max being highest, min being lowest, right? Okay. What do you think interquartile range means? The range in between the quarters, right? So from Q1 to Q3. So you find that using Q3 minus Q1. So the range in between the quarters.
And when you ask for range, you're never looking for an interval? You're always looking for just like one number?
So I think that if I want an interval, I'll ask you for an interval, but if I ask for the range, I want like a numerical answer.
Okay.
But I probably would give you partial credit for that because it was kind of just a misinterpretation of the question. Okay, and then standard deviation, if you guys, this maybe you haven't heard before, but this is a thing that describes the spread, spread, see it happened, of bell-shaped data. We sort of briefly discussed that sometimes things like take on this bell shape, and gosh, I wish I was better at art, but a standard deviation describes how spread out they are. So like that one versus, they're both bell-shaped-ish, right? But the one on the right is way more spread out than the one on the left, correct? And so this thing called the standard deviation measures that spread. We'll have a formula for that in just a second, but it's only for bell-shaped things. Okay. All right. So 63 college men were asked what they thought was their ideal weight, and here is a 5-number summary of the responses. 5-number summary of the responses in pounds, and they gave this information. So find the value of the range for these data. So this table, your book does this way, kind of similar. It just puts this median in the middle, and I couldn't make my program format that way, so it just didn't happen. So to do the range, what do you subtract? Max minus the min, and the max are the extremes, right? The absolute lowest, absolute highest. So the range is going to be 225 minus 123, which is 102. Okay, and it technically would be pounds, but I won't dock you for labeling unless I specify that you must label. Like, you can lawyer me. If I don't say you have to do it, you don't have to do it. Unless it's implied, but I'll respond to lawyering. Find the value of the interquartile range. So what minus what? So that's 45 pounds. Who's your math teacher? You can't subtract. 35 pounds. If you were high schoolers, you'd say, well, why are you a math teacher then? Maybe you're saying that in your head.
Yes,
Or
you
not,
would.
exactly. It's in your head. Okay, about what percent of men gave a response that falls into the interval from 155 to 190? About 50%. So they are the middle 50% because it's the space between the two quarters, right? Quartile 1, quartile 3. Okay. So we're going to make box plots again today, but we are going to also identify things that are outliers, and we're going to plot them in a different way on the box plot. So the first thing you should do is step 1, step 0. You should label your axis. Does that make sense? Like, give it some kind of, like, I'm counting by 10s, by 5s, and like make some tick marks or something like that. So tell your grader what your scale is. So the box part of it encompasses the middle 50% of the values, as in quartile 1 to quartile 3, okay? So draw a box with a lower end at quartile 1 and the upper end at quartile 3. It's like in your box plot, this is your Q1 line, that's your Q3 line up there. And you also put a line at the median, the middle value. So draw a line through the box at the median. You could call the median quartile 2, couldn't you? Like 1 quarter, 2 quarter? Okay. Calculate what I'm calling the IQR. What do you think that abbreviation stands for? Interquartile range. So that's going to be Q3 minus Q1. Okay. And we are going to, in this case, identify outliers, and the lines of our box are not going to go all the way to the outliers. And here's our criteria for outliers. So you take 1.5 times the interquartile range. It's like if my IQR was, let's say, 10, 1.5 that is 15, right? So if somebody is more than 15 steps below my quartile 1, that's the outlier. Or more than 15 steps above quartile 3, that's an outlier. But the judge is 1.5 times the IQR. If you're more than 1.5 times how far those middle 50% are apart, then you're strange. Yes?
It looks like we missed a section. I don't know if maybe I wasn't listening, but
Did I? Oh, yes, I added that. I said, and find, in this blank I meant to say 1.5 IQR. I was trying to be clever about also doing that step. But I didn't edit my slide. That's kind of loud. Okay. Mosquito. Yeah, so this 1.5 IQR is the thing you're going to use to figure out what are your outliers. So from your box, you draw a line in this direction until if your bottom value is less than this distance away, it goes to the bottom value. If your lowest value is more than that distance away, you stop at the next lowest value. And we'll have an example. It'll probably be a little bit better once you see it, okay? But you don't go further down below Q1 than this. And you don't go further above Q3 than the same amount, 1.5 times IQR. So you go down to that value, okay, you go up to this value, and there's some strange person, they're out there as a dot or a star. So mark the location of any data points that are not covered by these lines as dots and make them pretty obvious, like dark, so someone can see them. Okay, so I think we'll actually do one, and then the whole 1.5 IQR thing will make a bit more sense, okay? Because seeing some real numbers should help a little bit. Usually it does, right? Okay, so here are the weights for 9 men on the Cambridge crew team. Do you guys know what crew is?
Yeah.
You don't do much of that in Alaska because more than half the everything's frozen, right? But you know, rowing. So find a 5-number summary. So a 5-number summary means min, max, quartile 1, median, quartile 3. So looking for the min, the max, the median. We're looking for quartile 1 and quartile 3. Now all of these things probably going to be smart to reorder your data, yeah? So who be the skinniest person on this little team here?
109.
Every single girl here is jealous of that guy. Maybe not all of us, but you know, that'd be too skinny. Okay, who's next? 178's the next one, I think.
Yes.
Yeah, okay. And then, okay, great. 186, 185, okay. 186, right?
Yes.
188, 194, 203, and 214. Well, that one guy is twice the other guy, almost literally, nearly. One way I check and see if I've got them all is you can count them. Does that make sense? There are 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, and I said there were 9 in the beginning. Okay, so what's the min? 109. How about the max?
214.
Okay, how about the median? Is there a 1 value that is? Yes, there is. It's a,
186.
okay. So there's your 186. Now what you do to find Q1 and Q3 is you look at this part and this part, and you find the medians of those. So Q1 is the median of the lower stuff. Q3 is the median of the other stuff. And since you have this one middle value, you don't put it in either place. Does that make sense? 'Cause it's not clear which one it's supposed to go with. If you have 2 middle values, then you use them in this next step. Okay? So what would the median of the lower 4 values be?
163.75.
How'd you get it?
I added all those together and divided by 4.
That's the mean. You actually do 178 plus 183 over 2. Because you're looking for the median of that.
Those two right there.
Yeah, you're looking for what is the middle of this list. And since there are 4 values, the middle is the average of the 2 middles.
Okay.
Okay? So you're always doing, you did a median and then you're getting to a median of a median.
Yeah.
Okay? So you're always medians, no median.
Okay.
Okay. So for that, I found that it was 180.5. Anybody else agree?
Yes.
Okay, great. On the upper data, which 2 numbers do I average?
194 and 283.
194 and 203 over 2, and I got that was 198.5. Awesome. Okay, that is a 5-number summary. You get note cards on your quizzes because it's stats, and I can let you do that. 3 by 5. If you don't have a note card, just cut a piece of paper to the appropriate size. I'm not going to be mad at you. You need to know what some of this stuff is. So, like, you should know what a 5-number summary is. Know what things constitute that. Just go through your notes and write down things you think you need to know. Yes?
So will we get a note card for tomorrow?
Yeah.
Or we can make, oh, cool.
You can make your note card. Yep. So, just one. Yep. When you have tests, you'll get like a whole sheet of paper front and back. Okay, I wish you could make like using your note cards as guides. And so a smart thing to do would be to make your note card, and then after you had the test, like think, okay, I needed this, I didn't need this, and I should have had this on there and I didn't. And then when you get your test, you'll have like a good list of stuff you can put on your big note sheet. So, oh, systematic stuff, yay, logic. Who would have thought?
And most of the quizzes will have stuff related to the homework, right?
The quizzes are going to be stuff very similar to the homework, or notes done in class, which is awfully similar to the homework, right? Usually, it was pretty close.
There's literally answers from the notes.
I know, right? You should look at your notes. Okay, was there another question that I missed? Okay, so move. Find the value of the interquartile range. So IQR would be Q3 minus Q1, which is 198.5 minus 180.5, which is 18. Okay, awesome. So here's the part where we're going to find those outliers. So you're an outlier if you are either more than 1.5 times IQR above Q3 or 1.5 IQR below Q1. So let's find 1.5 times IQR, okay? So that'd be 1.5 times 18, which is what?
27.
Okay. So you're too high if over Q3 plus 1.5 IQR. So what was Q3 was 198.5, right? And then plus this 27 gives you how much? I got 225.5. Tell me if that's okay. Okay, so if you're above 225.5, you're considered an outlier. Is anybody bigger than that?
No.
So there's none on the high end, but there probably is one on the low end, right? Because there's that skinny guy. Yeah? And you're too low if you're below Q1 minus 1.5 IQR. Do you see that it's above Q3 a certain distance or below Q1 a certain distance? So that's going to be 180.5 minus 27, which is 153.5. So who's the outlier? And it's too low or on the low end, so to speak, right? So if this is the one criteria I know for judging outliers. Does that make sense? Okay, 1.5 times IQR above or below. So above Q3, below Q1. Okay. So now let's actually make that box plot. So my values range from approximately 110 to 220, right? I'm just going to count by tens. Do you hate it when you can't draw straight lines? Anybody have AFC like me? I did. Okay. Well, maybe nobody else does. 110.
Straight things to draw straight.
I don't think I can do that on my iPad. 60, 70, 80, 90, 200, 210, 220. I think that's right. I mean, ish. Okay. So first let's make the box. So the lower end of the box goes at Q3, or Q1, sorry. What's Q1? 180.5? So approximately 180 really, right? So 150, 160, 170, 180-ish. Okay. The upper end goes at Q3, which is, so pretty much 200-ish, right? Pretty close. Okay, and then you also plot the median. So the median was 186. This was 180, 190. So that's, the median's actually right there. Okay. Were there any outliers on the upper end?
No.
No, so in that case, you just draw your line from the box to your biggest person. And your biggest person is 214, so about halfway between 210 and 220, right? was there an outlier on the lower end? Yeah, that 109. So he gets a dot. And then your line extends instead to the next lowest value. So disregarding the 109, who is the next smallest person? 178. So you put your line over to 178. And there's a gap in between the whole 178 and the other guy. He's probably the guy who has to like yell at them to like, row, row, row. Right, good for them to be small because then you have to haul them around. Okay, is that all right? Okay, great. So just a little bit of vocabulary. Have you guys heard of percentiles before? Like you took your ACT and it's like, you're in the 65th percentile. And you're like, what the heck does that mean? I don't know. So here's what a percentile means. So the kth percentile is the number that has k% of the data values below that point. So if I took my ACT and it says that I was in the 90th percentile, that means I scored at or above 90% of people. Yeah.
Can anyone be at the 100th percentile?
That's a great, yeah. I don't know what that percentile means. You scored above everybody, so I guess probably, theoretically speaking, yes.
So if you're in the 90th percentile, you're then also in the 80th and 7th, and so on. Because that just means 90th, you could be the top.
So if you're at the 90th, you are at or above 90%. 80th, you're at or above 80. So if you're above 90%, you're also above 80% of people, right?
Mhm.
Usually you wouldn't, usually you would give this as the maximum percentage such that everybody is at or below you.
But if they were to count it among it, they would say, yeah, that person would count into it.
If they were saying you had to be above this percentile to like get into college, you know, like if you were, so they might use it that way.
Okay.
But what this really means is that the percentile you're at, you're like, if you divide everybody up is like in a line, you're above 90% of people. Or you could say also you're in the top 10%, right? So that's another way of phrasing it. So what percentiles are the first quartile, the median, and the third quartile? So what percent of data is the first quartile, like that Q1? That's the 25th percentile. So at Q1, you're at or above 25% if you're at Q1. If you're at the median, you're at or above what percent? 50th, yep. And if you're in the third quartile, you're at or above 75. That's the 75th percentile. So if you're in the 90th percentile, that means you are at or above the score of 90% of your peers. Means you're cool. Okay. So one sort of short little discussion topic that we have is, what do you do if you have outliers? And if you're going to disregard them, you cannot do so without really good reason to do so. If you do disregard them just because you feel like it, that's bad statistics and you're causing problems. Like, there's great story. I got interested in statistics. I started reading about health studies. And apparently there was lots and lots of bad statistics applied to the health advice given in the 80s when I was growing up. Dated myself then. So this guy, like, had these countries that he thought were super awesome and disregarded all other countries that didn't fit his hypothesis. That's bad science. Don't do that. So, but if there's a legitimate reason to leave something out, you can do so. So, you know, if it's a legitimate data point, you know, and it's just part of the natural variability, you know, then you can't throw it out. But if you have something that's drastically different, you could consider that maybe it's a mistake. Does that make sense? Like if I'm like measuring your height and I get someone that's 10 feet tall, maybe I made a mistake measuring that person. So it does, if you do have an outlier in your data, you could go back and look and see, okay, was there some mistake that was made? so that I could fix this thing. And then the other thing that could happen is that that individual you're looking at could belong to a different group from the bulk of people you're talking about. And a good example is in example 4 with the guy who is 109. He's probably not a rower, right? I think the official name for that is like coxswain or something like that. Yeah, I don't row, but so maybe that person is just not in the same group you care about. Like if we're measuring the average height of, I don't know, Scandinavians, and somebody in Scandinavia moved there from Japan, maybe we shouldn't count them because they're, there's a little bit different, perhaps. So that's another thing that is possible. So here we go. So refer back to the rowers of example, I guess that was example 4. If you want to describe the weight of all the rowers on the team, would it be reasonable to throw out that outlier of 109? And I think I would say yes, because he is probably not rowing and sort of does a different job than the rest of the team.
Which you would make a note in the data that you present.
Mm-hmm. Yeah, exactly. That would be really responsible reporting. One place this was actually quite apparent was I saw a little thing on the internet that had Simone Biles next to like one of the basketball players. Did you see this? It was hilarious. It was like, a 4-foot tall person and like a gigantic 8-foot tall person. It was like, I think that he was like twice as tall as she was. Almost. They're probably both outliers, right? Yeah.
So a lot of these kind of examples, you can argue whether it's
If you give me some logical, they should be a little bit more cut and dry since it's a class and a textbook and stuff. As long as you can support your argument with some kind of solid reasoning, it could kind of go either way. Okay, and what constitutes an outlier might depend on the context. So suppose a guy who is 78 inches tall, you might be like, how tall is that? I can't conceptualize. So 60 is 5 feet. 6'6". Okay, that's pretty tall, right? So 6'6" might be pretty tall here, but not among basketball players, right? Does that make sense? So can you give another example where the same measurement taken might be an outlier in one context but not another? And the only one that I have that I could come up with was myself in Japan. Not to pick on Japan, but I think that they're on average shorter there. And so I think that in Japan I'd be kind of tall, even though I'm totally average in America. And actually, who are the tallest people in the world? What sort of country has the tallest people in the world? Do you guys know?
French?
No, the Netherlands, the Dutch. Take a KLM flight and all the ladies are like a midget compared to them. So, yeah. Okay.
Good genes in there.
Yeah, or it's just, it's a group of people that sort of stayed together for a long time, right? And traits tend to show up over time. Can you think of any other examples where something might be an outlier in one context, not another?
Maybe ages in college?
Yeah, ages in college might be something. Maybe, college, you begin at a later age.
There's a lot of people who are coming into college at like 17 because they have.
Oh, that's a great idea, actually. Oh, I love this one. Good job. So, where I went to school, everybody was between the ages of 18 and 22 because it was a school that people went to almost entirely after high school graduation. So the median age probably was 20, right? Or 19, something like that. But at UAF, the median age is
I think 25.
27, I think,
Yeah.
actually. I think I've only recently gone above it. So the point is that someone who's an outlier at my school, Gustavus, would not be an outlier here. Because at Gustavus, a 25-year-old would have been like, oh my gosh, you're so old, why are you here? But here, since we have a much more diverse population, they're not outliers at all. So student ages at different college campuses. And I think that's quite different. So student ages at different college campuses. and I suspect that's true actually considering like most private institutions and state institutions. I think that's probably a common theme, that the median age is higher at state institutions than private schools. And Alaska's of course special because we have exactly one statewide system, right, with a few campuses. Not much to choose from, right? Okay. So next we're going to talk about bell-shaped curves. So bell-shaped curves. So in these curves, they look like, you know, bells. Ding dong.
So if there's like one, like let's say it's a box, it's a bar graph, and you have one that just, you have like a tall one, and then in the middle of them you have a short one. That's not a bell graph, right? Because
Well, it depends on how much data you take. So if your sample size is quite small, you might have an underlying bell shape, but not have enough points to actually observe it. Does that make sense? So what might happen is like you'll have a bar graph that's like, okay, that one dips down, and then that one goes up, and then that one goes up, and it's not perfect, but it's bell-shaped-ish. If you take more data points, it will become more and more bell-shaped. The more data you take, the more bell-shaped it could become. So it's a bit of a like guessing game to see if it is bell-shaped. You should always make a histogram or a plot of your data to see if it's kind of bell-shaped-ish, but you would really need quite a few points to get it to be completely bell-shaped. Yes?
what if there's more than one mode?
We're not going to worry about that quite yet, okay? Because we're doing the simple cases in this class, and I think that probably requires much more complicated statistics than we're going to cover. Yeah?
What's the difference between a histogram and a bar graph?
I don't think there's a super big difference, like they have sort of the same structure, but a histogram lumps stuff, they both lump stuff into groups, but the histogram,
Isn't it like a range versus?
a histogram does like a count, like this many, like as in this many out of the group, whereas the bar graph actually gives like the raw number of how many people. But they're not the same thing. Let me think about that more, because they're only a little bit different. They're really not all that different than each other, so you could use either one. And of course, how bell-shaped it looks will also depend on how wide you pick your boxes, right? So that also could influence stuff. So anyway, but the point with bell curves is most individuals fall where? In the middle, so in the center. And the farther a value is from the center, the less likely it is. Okay. So now we're going to actually learn a formula for standard deviation. You guys ready?
Service.
Yeah. Histograms are used to show distributions of variables, while bar charts are used to compare variables. I'm going to read this in just a second, okay? Like I probably can't process while you guys are all looking at me. It's just subconscious. Okay. So here is, so a standard deviation, when you have a bell-shaped curve, this describes the spread of the data, or how far things fall from the mean. And in calculating it involves a semi-long, complicated formula. Like it's not ridiculous, but it takes a little bit of fussing with to understand it. So everyone's seen a square root symbol, yes? Okay. So remember that this little sum bar means that you add them all up, right? So what you do is x bar is the mean, right? You find the middle value, you find the average, and you take x of i's, or all the other points you have. So you take the value, your first value minus your mean, and square it. Second value minus your mean, and square it, etc. And you divide by n minus 1, where n is your sample size. Now the reason that is what it is sort of complicated statistics that we're not going to go into, and I haven't actually learned yet. So, like, I will learn it probably next semester. So, and then you take the square root of the result. So we'll do an example with some specific numbers so you can see where it comes from. It's sort of it's a lot of button punching for now. And software does this for you also, but for now I want to make sure you kind of know what it is and you can actually button punch it out correctly once or twice. And notice how these two are related. S and S squared. They're almost the exact same, right? They really are the exact same. How would I get from this one to that one? What did I do? Square both sides. So this is kind of used, that's called the sample variance, which is used to describe the spread and shape of the data when you talk about higher powered statistics. But the thing that's useful is to first find S squared, and then take your answer and take the square root of it. Okay? And I'll do an example so you can see some specific numbers. So the first thing to do, find the mean, or X bar. That's going to be used in your calculation. So first find the mean. And then for each observation you have, your data points, you find the difference between X sub I, your actual point, and X bar. And then once you've done that, you square them all. Can anybody understand the reason why you have to square them? Because sometimes you're going to have a negative difference, and occasionally you're going to have a positive difference, right? If you didn't square them, what would happen to those negatives and positives? They'd cancel out, right? So this lets you keep track of, well, it treats a below by 2 the same as an above by 2 in some sense. And then values that are even farther away get more exaggerated by the squaring. Once you have this, you sum or add all those differences and divide by n minus 1, and then take the root. I'm going to kind of combine these steps. I think it's easiest to kind of combine those into one step and do one big punch in your calculator, and I'll show you how to do that. Okay. So in example 7, how about Dart? Let's find X bar. You trust me? I got it as 25, okay? Good to go? Seem reasonable? Okay. So I am going to find S squared. And to do that, you take first number minus the mean, square it. Plus second number minus the mean, square it. What next? Third number minus the mean, square it. And lastly, fourth number minus the mean, and you square it. Okay, and what are we going to divide by? N minus 1, which in this case is 3. Now here's where you got to be careful, okay? If you're going to punch this in a calculator in one go, as it's written right now, it's only going to divide the last number by 3. Okay, you want to add these all up first and then divide by 3. What do you need? Parentheses. And they're going to go here and then here, okay? And so I got S squared equals 18 from that.
Why did you divide by 3?
Because the formula for S squared is this sum X sub I minus X bar squared over N minus 1, where N is the sample size. And I had 4 things, so 4 minus 1 is 3. Okay, and so then how the standard deviation is the square root of this. So S is equal to the square root of 18, which is approximately, well, you could say 3 square root 2 if you feel really fancy, but let's give me a decimal. It's actually exactly 3 root 2. We have to do it in this class because there's stats. We can just use calculators. It's about 4.2, I believe. Do you guys agree with that?
Yes.
Approximately 4.2. Not so bad, right? Okay. Now, the area under a bell curve describes what proportion of people fall under that curve, and there's this rule called the Empirical Rule that's pretty helpful for figuring out how smart you are. So this rule says that 68% of the values fall within one standard deviation of the mean in either direction. So if you have your bell-shaped curve, 68% are within plus or minus one standard deviation of X bar. How much is, which means there's 32 left, right? And there's 16% that are below that and 16% are above, right? Also says that 95% fall within two standard deviations. And to prove this, you need calculus, okay? You find the area under the curve using something called an integral. You guys don't have to know that in this class. But the basic idea is that 95% are plus or minus two standard deviations away, which means 5% left over, and half of it's above and half of it's below, okay? And once you get three standard deviations, it's 99.7% of subjects fall within three standard deviations. So if you're more than three standard deviations away, you're really special. So that's really a great example. College students and sleep, because you're probably not sleeping much. So the typical amount of sleep per night for a college student has a bell-shaped curve distribution with a mean of 7 hours and a standard deviation of 1.7. So 68% sleep between 7 minus 1.7 and 7 plus 1.7. So 7 minus 1.7 is 5.3, right? And 7 plus 1.7 is 8.7. So 68% of college students sleep between those values.
Sounds about right.
95 would be 7 minus 2 times 1.7, 7 plus 2 times 1.7. So 2 standard deviations away is 3.6 and 10.4.
I got 3.4.
3, I'm pretty sure. 3.6 is right.
It'd be 1.7 times 2, right?
Yeah, and 7 minus that?
3.4.
That equals
Because
3.4 and then
7 times
subtract
2 is
this.
14.
So but 7 minus 3.4.
I got 3.6.
Yeah.
Okay.
Okay, sorry, no problem. Okay, and then this one is going to be 7 minus 3 times 1.7. So for that, I got 1.9. And then on the upper end would be 7 plus 3 times 1.7, which I got is 12.1. I don't know who those people are.
Lucky.
Lucky, yes. But if you're sleeping more than that, you're abnormal, right? Or less than 1.9, I feel very sorry for you, but you're probably playing too many video games. Okay. So, SAT scores. So the verbal SAT scores for students admitted to a university is a bell-shaped distribution with a mean 540 and a standard deviation of 50. So what is the SAT score such that only 16% of people had a higher score? So the middle 68% fall between, so the median is, middle is 540. Then one standard deviation above is 590, and one below is 490, right? And in that middle are 68% of people, yes? Which means how much is in this end and how much is in that end? There's 16% in both ends, right? You guys buy that? Okay. So what is the score so that only 16% of people are better than you? 590. See that? If you're at the 590, you're better than everybody except for that 16%. Okay. And the hint there is that 16 times 2 is 32, which is kind of the opposite of the 68%. 2.5%, twice that makes 5%, so that's the how many standard deviations away. That's the 3 would actually be That's 99.7, so 0.3 divided by 2. So one standard deviation away put us at 590 and 490. One more puts us at 640 and 440, thank you. So what's the score so that only 2.5% of people were below you? 440. Oh, okay. Can I just show you how to do example A in this next one then? Because then you can do all your homework if you can just do A. Okay. So with different situations, it's hard to say, like, big standard deviations in one thing. You might get big standard deviations in, like, SAT scores, but not in, like, hand widths, because hands are small things. Does that make sense? And a way to compare them is to do something called standardizing the scores. So that, okay, we can say you're 1 standard deviation away, or you're 2, or you're 3, or something like that. And to do that, you use this formula. It's called the z-score. You do the observed value minus the mean divided by the standard deviation that you were given. And this tells you how many standard deviations away you are. If you have a negative value, you are below the mean. So data values that are below the mean have negative z-scores. And if you're above the mean, you have positive z-scores. And we'll just do one. So suppose the amount spent on textbooks is a mean of 350 and a standard deviation of 100. Find the standardized z-score if you spend $300. So the formula is observed value. Which one's the observed value? 300 minus the mean, which is divided by the standard deviation of 100. 0.5, I think. Yep. So you're a little bit below average. Okay. One more thing, I promise, just one more. This last box. So if you're looking at z-scores, what are the z-scores of the 68% in the middle? They're how many standard deviations away?
1.
-1 and 1, because they're either 1 above or 1 below. How about 95? -2 and 2. How about that last one? -3 and 3.